Okay, so superposition principle and undetermined coefficients revised. So a lot of the times, especially in differential equations, we always revise some things once we learn a couple things going forward. That's going to be a lot of the sections going forward, except for the Laplace. That's going to be a little key thing. But this is a nice intro to Laplace transformations, which is a very big aspect in differential equations. So, what is a superposition? So the superposition principle basically says if I have two solutions, one for this situation and another y2 for this situation where it's the exact same, however, these functions are different. Therefore, the addition or subtraction with some constants in the front is a solution to this entire process. So what this helps us do is if I have two things, for example, let's say 3e to the t plus, let's say, sine of t being on this side of the equal sign, if I have a general solution to this one, if a general solution to that one, where the addition of them together actually is a general, particular solution to the entire process, which is cool. So that means we could break up individually. We don't have to do the entire thing at once, which is a bit painful to do. We could just split them up accordingly. Now, again, this is kind of nice because that's the one situation we could deal with. The second situation is, well, if I already have answers or solutions to one type of differential, I can have a scalar multiple of the others. And you'll see that what I mean by in a little bit. Okay? But like I said, this is a brief introduction to Laplace transformations, since Laplace uses stuff we already know to get stuff we don't know itself, or something similar to what we have already. Okay? So, how will we just break this down? Okay. So here's our, we want to find a particular solution to this situation. So we're going to call this F1 and F2 on our definition. And we're going to find a particular solution to each individual case. Okay? So first off, no matter what, we have to find the characteristic equation and just solve for it. So factoring this, so we get r is equal to -2 and -1. Okay, so if I follow this process, if I look at here, so just going back, so in this case, our m value is going to be 1, and our r value is going to be 0, and on this case, our m value is going to be 3, and our r value is going to be 1. Oh, sorry, 3. This is 0, actually. So it's power, right? We don't have a t power, so it's 0. Okay. All right, so if I follow this process, so r is not a root of this situation, so it's going to be our particular solution to this situation is going to be, and since we have m equaling 1, a1t plus a naught. And if I follow the same process over here, so m is 0, r is t, or r is 3, again, not a situation. So our particular situation here will just be able to form a0e to the 3t. Okay. Now all we have to do is find our coefficients in front, and we're actually done. So in this case, we'll just take the derivative of each one. So the derivative here will just be a1, and then the second derivative is just going to be a 0. So we plug these three values into our equation, we end up looking like this. Again, we're just looking for F1 so far. Okay. So plugging these all into it, we end up getting, or actually making our equations. So this is kind of nice. This gives you that. So it'll just be 2a1 equals 3. So a1 is equal to 3 over 2. Plug this into here, and remembering this gives you 0. So it gives you 9 over 4 plus 2a0 gives you 0. Bring it over and divide, and we end up being a naught is equal to negative 9/4. Okay. So this particular solution, following this process, I'll call that just a subscript 1, is equal to that. Okay. Now we do the same thing for f2. So we're taking derivatives each individually. And then plug it in back into our derivative. We end up getting, after a little bit of process, a0 is equal to 1/2. So this particular solution, we'll call it P2, is equal to 1/2 e to the 3t. So putting these together now, my real particular solution would just be the sum of these put together. Like that. Now that we know this, we can try doing this question. So same situation, is the exact same differential equation, but it's equal to something different. Okay. Now, if you notice though, these are just multiples of what we have. So for example, I can rewrite negative 9t as negative 3 times 3t, and I can rewrite 40 e to the 3t as 4 times 10 e to the 3t. Which means it follows this process up here. So this is where these k's come into play, these constants. Okay. So if I already know the initial one, and these are just scalar multiples, all I'm going to do is multiply each individual one by its respective k1 and k2. So if I go back up here, and I just rewrite this, so therefore, this part right here, I will multiply by negative 3, and this part here, I'm going to multiply by 4. So you actually don't have to do this whole process as long as we know that, that initial step here. Because again, they're just scalars of each other. So really, my particular solution for this situation will now be, we'll just multiply everything by negative 3. So negative 9 over 2t plus 27 over 4 plus 2 e to the 3t. And that's the nice thing about superposition is not only can we do each one individually, but if we know if it's a scalar multiple of something we already have, we could just use it in the process as well. Okay. Now let's talk about the initial conditions, solving for an actual initial value problem. Okay. So to solve for initial value problem with these kind of situations, we're going to put both the non-homogeneous and the homogeneous put together. Okay. So, and it basically summarizes is in this theorem. So given all these real numbers, and suppose yp of t is a particular solution to this, okay, in some interval that contains y1 and y2 that are, again, linear independent with the homogeneous equation, then there exists an initial condition such that this is true. Okay, so meaning we could solve for it. However, the biggest part we care about is what is the general solution going to look like before we solve for the initial condition. And that's going to be our general solution formula right here, or form itself. Okay. So how this breaks down is this is our particular solution, which we were dealing with, and this right here comes from the homogeneous part. So it's both put together. So these questions could be a little lengthy now because I have to do both, but that's going to be our general form of our solution. So let's put this to the test. So given y p of t is equal to t squared, so we're already given this part, check. So now we're just going to find this part here. So find a general solution and the solution that satisfies this. Okay, so we already have that part, so we don't have to do all that process. Now we just got to do our factoring portion. So first convert this to homogeneous part and just solve for r. So in this case, r is equal to plus or minus 1. So going back, that means we have our two solutions. y1 of t is going to equal to c1 e to the t, and y2 is going to equal to c2 e to the negative t. Here, e to the negative t. Okay, so therefore, putting everything together, our general solution is going to be our particular part, which is t squared, plus both put together. Like that. So that's the first part. We found our general solution. Next part is to solve for the initial conditions here. Okay. So that's simply just taking the derivative and just going for it right there, right? So since I have this here, we'll just plug in 0 in for t and then set that equal to 1. So that's gone, and this ends up being just c1 plus c2. Okay, so then taking the derivative of this process, and again replugging in 0 in for t, and this time it gets equals 0, so that goes away, and we just get c1 minus c2 now. So solving for this in this situation, right, we could just use well, we find out that they're the same if you really want to process, right? So the only way that process happens if they're both 1/2. So we get that. So finally, we have our answer. So now let's do one that's not so fun to do. So sine and cosine. Same situation above. Find the general and then find the solution that satisfies this condition. Okay, so unlike last time where we're given the particular solution, this one we have to find everything. And that's what takes a while to do. Okay, so either way we're going to have to find our homogeneous part. So this will be r squared plus 2r plus 2 equals 0. So you can't factor this, so just doing the quadratic formula, you eventually get this after you simplify. Now, just like we did last time, we're going to have to split this up into two parts. So we'll say f1 of x will just be the 5 sine, and then f2, of t, will be the 5 cosine. Okay. The nice thing, it's kind of mimicry one or the other as we go further. Okay, so in either case, we have m equaling 0, b equaling 1, and r equaling 0. Okay, however, if we go back a little bit, this is a solution, so in this case, r is -1 and b is 1. And it looks like we don't have it, so good. So we're just going to have our, I'll call this 1 for now. Yeah, for 1. No t is just straight values, which is nice. Again, this is just for this first part. No, but just basically the same thing for the second part anyways. Okay, taking the derivative twice, and then just plug it in to figure out what our a and b are going to be. All right, and then plugging this in into here, times e by 2, times I by 2, and set them equal to each one individually. Now this is the nice thing about being mirroring of each other. This is going to be the same no matter what. So your equation is going to be the same, but you're going to be solving for a little bit different. So what I mean by that is eventually, after a little bit of algebra, we get this. Sine it. Okay. Now at this point, because there's a 1 in front, or actually there's a 5, sorry, there's a 5 in front of the cosine, all of the, well, all the sine, all of this becomes equals 5, and this equals 0. Or actually, I could put this together, but I'll just write it down for now. And then these put together just becomes b. So this is for f1, but I can mimic exactly the same thing for f2 because it's just cosine. So this time around, this is a nice mimicry of it. Okay. Now simplifying, just solving for a and b individually here. So you get a is equal to 1 and b equals a negative 2. And on this process, again, just doing the same format, they just pretty much flip around. Just a is now positive. So for this situation, again, we're talking about just f. So P1 is going to be A is 1, B is negative 2. And over here, which is the same process, A is going to be 2, this is going to be 1. All right, so that's for our particular, and I'll see how we're going to do that in a little bit, but that's for our particular solution. Now let's go find our homogeneous part over here. Okay, so going back over here. Okay. All right, so this is not a solution to that, so therefore it's just going to look like this. All right, so how do we put everything together? So remember, when it comes back to our definition, it's literally everything added together. That means the individual parts. Remember, this P particular solution is everything put together. So it's going to be these two added plus that. Okay. So I'll write this first, and I'll talk about the rest in a little bit. Okay. So if I add these together, I can add the cosines together. So sine and sine is going to be 3 here. And then adding the cosines together, they just get some negative cosine. So this is our general solution. Okay. Now we solve for initial conditions. which is actually not as bad as you may think, because if you just plug everything to be 0 for t, and just remember a couple things for sine and cosine, things actually go away. Cosine of 0 just gives you the 1, so this ends up just being c1 here. And sine of 0 is 0, that goes away, that goes away, and this ends up being 1. So we find out that c1 is equal to 2. So that's not that bad to figure out. And then same process, taking the derivative, which is going to be a long process. Just remember when it comes to taking derivatives, this is technically now product rule. These aren't, but these are for sure. Okay. So, and then we plug it in, so we get 2 is equal, again, plugging all that process in. And eventually, after a little bit of algebra, we get this. Then you just plug in 1 in, plug in 2 in for C1. And just solve for C2. So this gives you end at 1. Subtracting it, we find out that C2 is equal to 1. Okay. So therefore, after all of this work, we could finally write our true equation. Okay, so let's see. So C1 was 2. And it's 1. And there we go. So very long process, especially when you're not given a particular solution. You have to find them all, and sometimes it's very, very, very lengthy to do so. Okay. All right. So let's keep going. So that's very long to do. Wouldn't it be nice to have a general solution for sine and cosine? And that's where this revise comes into play. So we're revising our particular solutions for sines and cosines instead of doing all that horrible mumbo jumbo and put everything else initially together. Okay? So if we have sine and cosine on the right hand side, where p and q are polynomials of degree n and m respectively, so not the same degree, so opposite, 5 and 4 or 2 and 2, things like that. Therefore, our general form of our particular solution will look like this. And it looks very, very, very long to do. But it's just a combination of both the initial parts and the sines and cosines parts. That's why. However, one thing you got to be very careful is this k value. This k value is the larger of the two powers we started with. Okay. So let's try doing this process. Now the best part is we're just going to find the solution form. We're actually going to be solving for it. We just want the form of what's going to look like. Okay, so we can just use the arbitrary letters for this case. Okay. But in either case, we're still going to have to solve for our particular solution no matter what, our characteristic solution. So again, not factorable. So after quadratic formula, we get that again. Okay. All right, so therefore, let's see, let's see what we have. Okay, so we have this one and that one. So we have b to be 1. We have r to be -1, so that matches. B1, so it is a solution to our characteristic equation. And now we want k. So k is the highest power, so 3 and 0, so it's going to be 3. So since this is a solution, it's going to be a 1. And since k is 3, we go to 3, 2, 1, 0. negative 1 because of the r, and then just rinse and repeat for the sine part. B is 1. Oh, and then there we go. All that is our actual answer. Very, very painful. Okay, now, the nice thing about the superposition principle is now we could do stuff like this and it doesn't look like a horrible mess to deal with, okay? Because just like a train, we could just add it on top. So this part here, it'll call F1. This part right here will be F2. And this part right here is going to be F3. So we can do each one individually and then just put everything else together. Okay? So we're just going to do exactly that. So we'll do the first part. Okay? So in this case, we have R is to be 0, B to be 1, and K 0. I think that's all we need. For 3, R is 0, N is 0, and that's it. Okay. And then for the last one, we have M to be 1, and R is negative 1. Okay, so now we're going to solve for a characteristic equation, and this is going to be, now it's to the third power, so factor in an R, and we get actually this, believe it or not. We get a duplicate. So we get R is equal to 0 and R is equal to negative 1, which is going to be useful right here and actually there. Okay. All right, so again, we're just going to do each one individually. So we'll just start here. All right, so we don't have any imaginaries, so it's just going to be a naught e to the negative 1 power. Okay. That's the first part. Second part. Now, because it is a is a root, therefore, if you remember, it's going to be t times m is 0, so just a naught. Okay. R says 0, so we don't have any e's there. Okay. And on this side, it's also a root, and it's a double root, right? This is a double root. So this is going to be t squared, and then m is equal to 1, so a1t plus a naught t raised to the e to the negative t power. And now we just put everything together to find our particular solution. And I'll just go straight down with the alphabet. I'll leave this in there. And there we go. pretty lengthy process, but if you notice, as long as we just break those stuff individually and do the rules again individually, it's actually not that bad to just define the form of it. Define the actual particular solution, that's a different story.